Greetings everybody. Let's take another look at vector line integrals. So kind of other notation that you might see if you encounter these things other places, you might see something that looks like the line integral over the curve C of f dot t ds. Now what the t is meaning is just our unit tangent vector, ds is then our arc length form, and so TDS is really just looking at r prime over the norm of r prime times ds just being ds dt times dt. Well, remember when we did that, the derivative of s with respect to t was just the norm of r prime. And so what happens in that case, our norms cancel out, and we end up with r prime t dt, but that was just our usual old dr. And so when we're doing this, we're really doing the exact same thing as if we were doing the f dot dr. Other things that we might see instead of the TDS, we might just see that as just the vector ds. And so the vector ds is just really meaning this TDS, which is the same thing as our f dot dr. Okay. Now, kind of one nice property about these line integrals is that suppose we've got a curve C1 that goes from P up to Q, then we've got another curve that goes from Q over to R, and that's our C2. Well, what this really does is really give us a path from P all the way over to R, and we can kind of denote that by C1 plus C2 being this curve, which is really just saying first you do C1, then you do C2, and then you get from P over to R. Well, with our line integrals, this gives us the line integral over our entire path from P over to R is just our line integral of C1 plus C2, but then that distributes and kind of splits apart into the natural way of our line integral over C1 plus our line integral over C2. Kind of another thing that went along with these parameterizations is that remember we could get the opposite orientation. That when we had a parameterization, it gave us a direction in which we were tracing out that curve. And so if we had our curve C being r of t, just x of t, y of t, z of t, with t going from A over to B, then we can give it the opposite orientation, and sometimes we'll denote that with just this minus c that's on it. So this just being the opposite orientation of the curve C. So we've got r of t, just replace t with negative t on the inside. So we've got x of negative t, y of negative t, and z of negative t, with now t going from negative b up to negative a. And so what happens in that case, we get our line integral over negative c just being the integral from negative b up to a of f, x of negative t, y of negative t, z of negative t, and then our dr, but our dr was just going to be dx dt, dy zt, dy dt, dz dt, evaluated at negative t because we were doing the chain rule, times the derivative. So this was the derivative of the inside, evaluated at negative t, keep the inside the same, times the derivative of the inside gave us that negative dt. So if we just take this expression and then do a substitution with u is equal to negative t, so that du is just going to be negative dt, then this gives us the integral from when t is negative b, u is going to be b. When t is negative a, u is going to be a of f of x of u, y of u, z of u, dotted r prime of u du. Well, if we want to reverse that integration, then that's just going to give us a negative sign for our integral from a to b of this expression, which is just our usual integration for our original curve C, introduced by, and also introducing this negative sign. So kind of two properties that we have in that case is that the integral over the negative, over the opposite opposite orientation of our curve just introduces a negative sign when we do the line integrals. We can split curves up as C1 plus C2 being distributed across those integrals, so the integral over C1 plus the integral over C2. So this kind of gives us a couple of properties that we can use kind of in our final discussion of vector line integrals, and I will see you guys then.